Okay, welcome to your session on data analysis and interpretation for the Sport and Exercise Biomechanics module. First of all, you'll perhaps notice that I'm not using PowerPoint for this particular video lecture. I thought I'd try something different and go with, and go with a session where I draw using paint. Does this mean I'm better than the Khan Academy guy? Well, I think the picture there speaks volumes, doesn't it? So the aim of this session is not so much to talk about the statistical analysis side of things, because you would have covered that in bespoke modules, although we will touch on it, but is to talk about what to do with the data in terms of interpreting it. Once you've done your stats test, what does that mean? What does this data mean? That will vary potentially for each of you, but nonetheless, this should hopefully point you in the direction that you need to go in order to understand what you're supposed to do with the data once you've analysed it. So, first and foremost, it is essential that you have a clearly defined aim and set of hypotheses. And I appreciate this is going back a few steps, but if you understand your aim clearly and you have that stated where it should be at the end of your introduction section, then you will find it that much easier to write your report. What I tend to do whenever I'm writing up a research article or anything similar to this is I will write my aim, obviously where it should be in my report, but at the same time I will include it, or I will jot it down on a post-it note and stick it on top of my monitor on my PC so that I have something to constantly refer to, and this helps you with your reading. I find it's very easy with this topic to drift away from what you actually did. The reason I haven't added too many papers onto Brightspace about your research topic is because there are thousands of research articles out there. You simply have to go to PubMed or any journal database, type in your chosen research topic, and you will be greeted with a plethora of potential papers. But it's up to you to sieve through them and to filter through them. You'll need to do some wider reading in order to do well at this, so your reading should be guided by the aim of your study. You'll want to read studies that have a similar aim to yours. Admittedly, your study is on a much smaller scale, but nonetheless you will want to look at studies that have got a similar aim. They might have done other things in their study design, but as long as there are some similarities, then the paper is potentially worth reading. So the aim, if I was to write up a study similar to yours, would possibly be the aim of my study is to, or sorry, not the aim of my study, the aim of this study was to compare the sagittal plane mechanics between bare or lower limb mechanics. Let's try that again. Let me try jotting it down. There we go, much better. So to compare the sagittal plane lower limb mechanics between barefoot and shod running. Obviously you collected data from the frontal plane as well, so you have that option. But your aim is specific to your study, but still not as specific as your hypotheses. So your hypotheses are a set of predictions, as I'm sure you know, and these are essentially as specific as you can get to your study in terms of this is going to be a prediction of what you think will and won't happen. So my null hypothesis might be, for the study of which I've written up here, there will be no statistically significant difference between the sagittal plane kinetics and kinematics of the ankle, knee and hip between barefoot and shod runners. Something like that, something in that realm. Doesn't have to be that, obviously, but if you understand your aim, you have a better chance of producing a good quality report, because it's the foundation of your report. Okay, so let's just briefly move on to your study design. And again, it's important that you have this clear. I know that you were the ones that collected this data, but that was some time ago now, so it's important to just recap this information, I think. So, your study design involved, I've just drawn here 5 participants as an example, but obviously you used considerably more. But your study design was one in which the same participants experienced both conditions, or both experimental conditions. So you may have, for example, let's just take this down. Condition 1. Oh, how pocket time. And condition 2. And what I've also added here is the corresponding participant number. So we've labelled each participant a number from 1 to 5, and that corresponds with the values we see here in our makeshift table. So P1 would be the data for this participant here, P2 would be the data for this participant here, P3 data for this participant here. We'll just make up some data now. So let's say participant 1 got 3 for this particular measurement, doesn't matter what it is. Second one got 3.2, the next one got 4.2, participant 4 got 3.8, and participant 5 got 4.1. And of course we would have the same for condition 2. Okay, so this is the, I wouldn't call it raw data, because the data that you collected when you were in the laboratory was the raw data. You then processed it slightly, particularly the kinematic data. So this is the semi-raw data, I suppose you could say. Let's say this is the, I don't know, ankle flexion angle at initial contact for each of these participants. Between condition 1, let's say barefoot running, and condition 2, shod running. But this could equally be barbell deadlift, hex bar deadlift, front squat, back squat, whatever it may be. Now you have the same participants undergoing each condition. So these values here, so for participant 1, in condition 1, they got 3, in condition 2, 5.6. For participant 2, in condition 1, they got 3.2, and for condition 2, they got 4.9. You see where I'm going here with this. So, it's very important that what you don't present in your results section is this, the raw data, or semi-raw data. What you will do is you will get a mean value for each of those conditions, condition 1 and 2, which are whatever they are, again, say barefoot shod running, and it is those values, those means, that you will present in your report. So let's work those out quickly. Okay, so 2.9 for condition 1 and 5.5 for condition 2. And it doesn't matter what this is. This could be joint angles, could be ground reaction forces, doesn't matter. These values here, which I'm going to crudely draw around. Ooh. Let's get a box or something. There we go, that's much better. These values are what you are going to use for your statistical analysis. Okay, you do not present them in the report. We do not care about the individual participants' data. Obviously, these will have been averaged over each trial that the participant performed. I forgot to add that earlier. But this is each participant's data. We don't want to see this in the report. But you will use this for your statistical analysis. Now, I'm not going to go over the details of how to do this. I appreciate some of you have been in contact about this because you don't have access to SPSS, but you can still do the test in Excel. It will give you the exact same answer. Excel is fine for basic stats testing. And with actually just saying lazy, it's something that you can very easily look up how to do. As long as you know what the statistical test is that you need to do, and we've mentioned this, just Google that with the word Excel at the end and you'll find a plethora of information on how to perform this test. So there's really no need to go over this in any great detail. But this in blue is what you will use in your statistical testing. What you will include in your report is, surprise, surprise, the mean values here, with, of course, the standard deviations. Standard deviations for this makeshift data. Plus or minus 0.5 for condition 1, plus or minus 0.4 for condition 2. Now, just to show that I'm not being difficult, I will give you the equation. Again, it's very easy to look up if you simply go to Google and type in standard deviation Excel, but there are two types of standard deviation, so to avoid any confusion and lots of emails for me, I'll give you the equation that you need here. You simply select a cell underneath your column of data and type in stdev dot p, and the dot p is the important thing. You then open brackets, you select your data. Don't type in select data, I'm just saying that's what you do. You close your brackets and you press enter. Again, don't type enter into the equation. You would type in equals stdev.p brackets, and then I would drag and drop my data in this column. I would then close brackets and hit enter. Okay, and that will give you your standard deviations in Excel. So the main data that you want to report is the mean values for each condition, standard deviation for each condition. There are other data that you can include if you so wish, but it's entirely up to you. And of course, the p-values. Is the data significant or not? And the p-value only needs to go to 2 decimal places. You don't have to put 0.000000147892456 or anything like that. And you can simply indicate that the data was significant by, if you've made a table, by putting a little asterisk like that at the top of one of your data columns. So that would suggest to the reader that there is a significant difference between these two conditions, and you can state what the p-value specifically was in your text in the results section. Okay, so hopefully that's enough to help you out with that side of things. So let's consider which data to include and which kinetic and kinematic data pairs appropriately together. So it's entirely up to you. I know I'm beating a dead horse here, but it's entirely up to you what data you choose to use. You've collected data from the sagittal plane, as I've tried to represent here. So here's the hip, knee and ankle. And you've also collected data from the frontal plane. And as if by magic, there it is. So you don't have to use all of the data that you have. It's entirely up to you, but you must use some kinematic and kinetic data. You have to use some. You can't just use all the sagittal data and ignore the force data. Likewise, you can't just use all the force data and ignore the kinematic data, the joint angle data. So you've got an array of kinematic data. I won't go through it all, but you've also got your ground reaction forces, and here we have a representation of the vertical ground reaction force. Okay, so we will call this ground reaction force V. He says. Try that one again. There we go, seamless transition. So the vertical ground reaction force. Now, this force is applicable to either plane of motion, because the vertical ground reaction force is your upwards force. So this would be relevant to include whether you're looking at the sagittal or the frontal plane data. However, if you're looking at the sagittal plane kinematic data, then your choice of horizontal ground reaction forces will be potentially, or should be potentially different. So for the sagittal plane, it makes sense to pair your kinematic data with the anterior-posterior ground reaction forces. So this red arrow on the right hand side here would represent the anterior ground reaction force. This one on the left would be the posterior ground reaction force. They wouldn't occur simultaneously like this, but just for the sake of example, because they're occurring in the same plane, if that makes sense. They are occurring in the same plane of motion. You can include the medial lateral, but it's just going to be harder to link those together and link those with the sagittal data. Likewise, if you were to use the frontal plane kinematic data, the medial and lateral ground reaction forces would be appropriate to include. So if I draw a line here that represents the midline of this person, so an imaginary line just drawn down the middle of this person running, fairly straight, then this green arrow on the left would represent the medial ground reaction force because it's acting medially, and this green arrow on the right would represent the lateral ground reaction force. And again, this makes sense to include because it relates to motions like ankle pronation and supination, which is a medial lateral movement, or knee valgus varus, hip abduction, adduction, all that good stuff, whereas the anterior posterior ground reaction forces relate to the acceleration and deceleration, which is basically the propulsion and slowing down of the body, and we'll talk about those in a bit more detail in a moment. And so they just pair together well. You can, if you just decide to use the sagittal data, you can include the medial lateral as well. It will just be a bit harder to relate those together. Of course, if you were feeling particularly heroic, you could do it all. Frontal, sagittal, kinematics, and all the ground reaction forces. Okay, so let's move on to another important point and something to bear in mind with regards to your study design. Your kinematic data, this is your kinematic data, was collected at initial contact, the moment your participant's foot came into contact with the ground. And we don't call this heel strike or forefoot strike in this case, because we don't know what's going to happen, because you're assessing barefoot and shod running. We're not sure. Maybe they'll forefoot strike, maybe they'll rear foot strike. Who knows? Therefore, we use the term initial contact. However, your ground reaction force data is from slightly later on in the gait cycle. It's a standard force time graph, the sort of graph that you would see on our Kissler force plate, and we've obviously force up the y-axis, time on the x-axis, and I'm going to attempt to freehand draw, this is going to be terrible, a standard, oh look at this, it's not actually too bad. Ah, I've deleted it! Idiot. It was going so well. There you go, not bad, could be better, could be worse, bit of a slant to it, but you know, you can't have everything, can you? Anyway, I digress. Your kinematic data was collected at this point here, at initial contact. Okay. However, your kinetic data was the peak vertical ground reaction force for each condition, or for both conditions, I should say. And that, what colour will we go for? Let's go for a nice green. And that obviously would occur here. This is our peak ground reaction force. Okay. So, it's important that you acknowledge this in your method section, and that you understand that this is what you did, and the reasons why. You are trying to see if wearing shoes or not wearing shoes when you run alters your body position here, which in turn causes a change to this value here. Okay, so slightly down the line, as it were. Obviously this is a very short period of time, this will be milliseconds, but you get the idea. And it's just, this is only a brief aside, but this is an important thing to bear in mind, because so many students overlook this who choose this project, and it's important that you don't, and that you bear this in mind in your discussion section. So let's move on to thinking about what our data may potentially mean once we've done our statistical testing. So what I have here in this little makeshift table is our two conditions, barefoot and shod, some kinematic data for the hip, knee and ankle, so the flexion extension at initial contact for each of these joints, and the kinetic data, vertical, anterior and posterior ground reaction force. Now, this is very much an idealized set of data. There's no standard deviation. I've just jotted down some numbers, basically. But this is sort of perfect scenario, I suppose you could say. So first of all, it's worth considering, what does this mean? And sometimes it's worth drawing, exactly as I'm doing here, out your data. When I first learned the principles of physics, my teacher would say to me, you can look at the numbers all you want, you can look at the calculations all you want, but one of the best things to do is to actually draw a little sketch of what you think is happening to help your understanding. And I've always been a very visual learner, if that's such a thing, and I find that very useful. So let's draw our idealized scenario here. So we have SHOD, which is our condition that we have here. We'll focus on the kinematics first. So this is our SHOD condition. This is this information here for the ankle, the knee, and the hip. So for our barefoot condition, we see a slight increase in our knee flexion. Knee flexion. The anatomy is strong today. Hip flexion. There has been an increase here. Very small one, but an increase nonetheless. Okay. Let's draw in our knee joint again. I won't bother putting the label in, you know it's the knee. Let's bring the size down as you were. So there's been an increase in hip flexion, okay, which we can see here. Okay, so the knee. 25 degrees of flexion in barefoot, 12 degrees of flexion when shod. So okay, there's an increase in knee flexion. If the hip is in this position, then the knee will have to be here. Something like that. So we're comparing this to this. So this, in this condition, when we say knee flexion, we're basically talking about the position of the lower leg relative to the upper leg, so the tibia and fibula relative to the femur, the thigh. So there has been a significant increase in knee flexion in our SHOD condition. And if we draw the ankle in here, the ankle is a negative value, suggesting that it's an extension. This ankle here in our first condition is in 2 degrees of flexion, that's dorsiflexion. This is in 15 degrees of plantar flexion, so that would be here, like this. So these are our differences in our two conditions overlaid. Sometimes they don't work well overlaid. Maybe this should have been side by side, but never mind. But this is our these are our kinematic differences. So let's say that there was a significant difference between, I won't draw the little X's, but let's say there was a significant difference here and here. So this difference at the hip existed, but it wasn't significant. Therefore, we don't discuss it, and that's a very, very important point. If you find, and I'm sure some of you know this, and I'm beating a dead horse again, but if you have non-significant data, i.e. the p-value is greater than 0.05, and you look at it and think, yeah, but there's a 3-degree difference there, doesn't matter. The statistical test that you have done is essentially looking to see if the variable that you have changed, in this case wearing shoes or not wearing shoes, caused the difference that we see in the values here. If the p-value is greater than 0.05, then the answer is no. And any difference that we see is purely due to natural variation or chance or some other random effect, but it is not because of the condition that you changed. Therefore, for the sake of your discussion, if you have non-significant data, so this is p equals 0.8 or 9, let's say, so fairly insignificant, you consider these values to almost be identical. That's the best way I can think of describing it. You just treat them as the same. There is no difference. You don't even acknowledge that the difference that's there might be due to chance or natural variation. You just say they're the same. There was no statistically significant difference. Okay? So these are our two significant values at the knee and the ankle. Okay, good stuff. It's between all of our kinetic data. So our job now is to think, okay, what differences have occurred? It's fine to see a significant difference, but you have to consider which is greater and which is lesser. Where is the difference? So the barefoot condition has produced a lower vertical ground reaction force, a higher anterior ground reaction force. So let's draw this in. Oh, wrong one. So this is lower, and when I've had lots of data to work with, I've done things like this. This is higher, obviously, and this is lower. Okay, and the same for our kinematic data. So we have an increase here and a significant decrease here, but no difference in the hip data once again. So we have to think about, what does this mean? At initial contact there was a significant increase in hip flexion and ankle extension that seemingly resulted in a reduction in the vertical ground reaction force, an increase in the anterior ground reaction force, and a decrease in the posterior ground reaction force. So, one thing we could say is, okay, so we're thinking about, sorry, just to go back a step, how did this cause a change in this? That's what we're getting at. So, one thing we could potentially say might be, means a reduced loading on the lower limbs in that transition from initial contact to the peak vertical ground reaction force. It doesn't mean that the force was lessened. It might mean that it's just spread out over a greater period of time, which has caused that reduction. So same amount of force, just spread out over longer. We haven't collected that data, so we don't know, but that doesn't matter. But this is our loading force. This refers to how much inertial force is being absorbed up the lower limb, and if that's reduced, that may have potential benefits for reducing the risk of injury and factors such as that. So, the anterior ground reaction force, what can we make of that? Propulsive force, and there are various studies out there that look at the influence of the anterior and posterior ground reaction force on the acceleration and deceleration of a body in motion, and the importance of increasing the anterior and reducing the posterior. So again, conversely, I shall type this one out as you see it, reduced, or a reduction in the ground reaction force posterior, or posterior ground reaction force, means a reduced braking force. So this is what would slow you down. This is, I mean, it's always going to be there to some degree, but there is less of a braking force, more of a propulsive force. So we could put a performance-based slant on our discussion by talking about the two horizontal ground reaction forces. So this could have a more performance-based discussion. So this might be beneficial for runners in the long term, because greater anterior greater action force means more propulsive force, reduced posterior means reduced braking force, so on. The vertical ground reaction force, we could put a more clinical health-based, well, perhaps not clinical, but health-based discussion on, meaning perhaps reduced injury risk, perhaps a reduction in loading is going to cause a reduction in, or repetitive loading I should say, is going to cause a reduction in repetitive stress injuries. Thanks to this increase in knee flexion and decrease in ankle flexion, or increase in ankle extension, whichever way you want to look at it. So there we go. That would just be a summary. We also have to consider, well, why has this occurred? We've explained how the kinematics have caused the subsequent kinetics, but why did this occur? Why did these changes here? We can't ignore that. Take a moment here. So this session will be shorter than is usually advertised, because this was supposed to be more of a discussion and I would pause and ask questions and things. But perhaps take a moment here to pause the video and consider why knee flexion has increased and ankle flexion has decreased between these conditions, why that might be. If you think back to week 1 or 2, which might help you if you review our lecture slides from week 1 or 2, it could be due to proprioceptive reasons. So, tell you what, let's type that out. So proprioception. Remember, this is our body's ability to be aware of limb positioning in 3D space without having to obviously look at our limbs. Now, if you do find a significant difference in your kinematic data, you don't have to define what proprioception means. We know, but you can still talk about what it means for your runner. So we have proprioceptors, specific parts of our nervous system which allow this sense to be processed. Now, as we've said before, when we run with shoes on, very often we will heel strike, because consciously or unconsciously, usually unconsciously, the body acknowledges that there is this big squidgy heel on the base of the shoe, or there should be, which means you can heel strike, and that squidgy sole to the shoe will absorb some of the impact force, and therefore it's safe to strike the ground with the heel. But of course, if you look back at the diagram here, we've got the hip in the position it's in, the knee is almost at full extension, the ankle is more or less neutral, just slightly flexed, but this is a very rigid position to land in. And the barefoot condition, is a far more mobile position to be in, where the forefoot comes into contact with the ground, and from there, as the forefoot contacts, the rear foot comes down as the knee as the knee extends. This increases the impact time of our body coming into contact with the ground. And we assume this position because of proprioceptive reasons. When we take our shoes off, and you can give it a go, try going outside, find obviously social distancing where appropriate, and taking your shoes off and just try running on some concrete for 5 seconds. You won't hurt yourself, but you will forefoot strike, I guarantee you. Otherwise you'll do a lot of damage to your ankle. Your ankle does have its own natural shock absorbers built in terms of little stores of fat in the sole of your foot, or in the heel of your foot, but still, that wasn't evolutionarily developed for running on concrete. You will adopt a more forefoot style of running, and this is thanks to proprioception. So this could be a reason for our differences in our kinematic data, which has then gone on to cause a change in our kinetic data. We've built a full picture of this. We now need to, good God, what an awful error, it's going wrong, I'm going to stop. We now need to do some reading in and around the literature and compare our findings to the findings of other research articles and what other people have found, see if they agree, see if they disagree, who knows, it doesn't matter. But the main thing is that we compare to what others have found. So we might say, I don't know, Watson et al. Found a reduction in the vertical grain reaction force when running barefoot, the same kinematic data but no change in the anterior posterior. Well, why might that be? That's where you need to look at their methodology, what Watson et al. Study did compared to your study design. Maybe it has something to do with the fact that, I don't know, maybe Watson's study, this hypothetical researcher, was conducted on a running track or on a treadmill that had a force plate in it, whereas you had to run over a short 10-meter runway. So there are things like that to factor in. The most important thing I can say for your discussion not to do turn their discussion, oh, I hope I could spell discussion, ignore that, you get the idea. Do not turn your discussion section into a limitations section, by which I mean acknowledging your p-value at the beginning and what your statistical outcome, and then basically spending the rest of the discussion saying, well, this was wrong, this might have caused a problem, this was an issue, we could have done with more participants, blah, blah, blah. That's not what a discussion is. You're supposed to discuss your results and what they mean, not what's wrong with them. You can acknowledge some limitations at the end of your discussion, but this needs to be the smallest section in your report, a tiny section. And please do try to be more original than we could have, or the study could have benefited from having more participants. Every study wants more participants. That's a global issue. You can never have enough unless everyone on Earth is taking part in your study. You haven't got enough participants. So try to be more original. Try to come up with something more interesting than that. Or maybe you don't have to put in a limitations section. I know what your limitations were to this study. It would be far better to use that word count to continue to discuss your results. I would not mark your work down if it didn't have a limitations section in your discussion. I really wouldn't. But the important thing to remember is just because your data doesn't come out as significant, if that is the case, so if you get insignificant data, your study, and this doesn't mean that you don't have anything to talk about. What this means is that barefoot and shod running are comparable to each other. They are the same as far as your study is concerned. Forget the limitations, forget your study design. Your results have shown that your results have shown that barefoot and shod running are the same. Now, you can talk about the implications of this, but also then you can acknowledge your study design in a non-critical way by saying, well, this may have occurred because of the length of running. So again, it was only over 10 meters. You collected data at roughly the 5 meter mark. So this is perhaps a case of barefoot and shod running are comparable over short distances, but in comparison to other studies which have looked at longer distances, and you can then do that. Look at studies that have used force plate treadmills, look at studies that have just used standard force plates in a running track and have looked at longer distances, and look at studies that have looked at short distances. There are some out there. But this does not mean that your data is meaningless. It means that your conditions are comparable, they are the same. And this means that you can recommend barefoot and shod running equally. You, as far as you're concerned, have solved the issue. There is no difference. They're the same. Move on. You wouldn't do this in research. You'd obviously do more studies, but hopefully that makes sense. It doesn't mean that you don't have anything to talk about. Okay, well, I hope this session is useful, and as ever, if you have any questions or queries, do feel free to get in contact. This is, as I say, a bit shorter than is advertised, but it was supposed to be a slightly different session, but at least you've got the main content and hopefully everything you need to write a good report.